So today we're going to talk about questions from homeworks on section 6.1. We're going to talk about number 6, and 6.2 we're going to talk about number 4. So for section 6.1, number 6, we're asked to find the area bounded by all of these different curves. So the first function that we're looking at is the function y equals 2 divided by x. Notice that this is very similar to the function y equals 1 over x, which has, here, I'll draw a picture to get us started, has a behavior that looks something like this, but it's going to be twice that because of the coefficient of 2. Let's plot some points. When x is equal to 1, we see that our functional height is going to be up at 2, whereas when x is equal to 2, our functional height is going to be down at 1. And we know, you could also graph it on a calculator, that your function will continue with a shape something like that. So that's our first curve. Our next curve is the curve y equals 8x. It's just a slope of 8. It's just a line. And then we have a line with a slope of 1/2. And again, this isn't exactly to scale, I suppose. But I do know that with a line with a slope of 1/2, you're going to be going through the point 2, 1. And we want to look at the x values that are greater than 0. So it means that we're examining the area of the region. I'm going to color in blue. But this is a tricky region. This is a tricky region because we have 3 different functional bounds. And we need to split this up into different pieces to be able to account for the fact that for this, at the start of this region, we have the function y equals 8x as the top function, and this linear function is the bottom, whereas for this part of the curve, the function is 2 over x on top. So let's just start by finding some of our intersection points. We're going to need to know where these curves intersect in order to able to get the accurate boundaries for our integrals. I know just from mental arithmetic we can see that 0, 0 is one point of intersection down here where the 2 lines cross. Let's see where the next point of intersection is. That's where the line y equals 8x is exactly equal to the line where y equals 2 over x. And we can solve that algebraically by setting the 2 functions equal to one another and solving for x. So this means that 8x squared is equal to 2. That means that x squared is equal to 2 divided by 8, which is a fourth. And that means that x is going to be equal to plus or minus square root of 1/4, which is the same thing as plus or minus 1/2. Notice that in this domain we want our x values to be positive, so we are going to ignore the value where x equals negative 1/2. And that means that our intersection point right here is where x equals 1/2. And plugging that back into the function, 2 divided by 1/2 is 4. So we found one of our intersection points. Let's find the second intersection point on a new sheet of paper. So the second intersection point is going to be where our curve y equals 2 over x is set equal to our curve y equals 1/2 x. So setting these functions equal to each other, 2 over x is equal to 1/2 x. I'm going to multiply both sides by x and multiply both sides by 2. And I see that I get x squared is equal to 4. And that means that, again, I'm going to ignore the negative value because we want to restrict our domain to positive x values. So 2 equals x is our intersection point, which we can see graphically. That makes sense. And if my x value is 2, we already saw that 2 divided by 2, our y value will be 1. So this gives us a start of the bounds, and now we can actually break up our region into pieces. We're going to do this as 2 separate integrals. Let's talk about integral 1. I'm going to divide it using this red line. Maybe I'll extend the red line down. And we know that the x value is x equals 1/2. And so we're integrating as our x values go from 0 to 1/2. And And the upper curve in this case is the curve 8x. The lower curve in this case is the curve 1/2 x, and we're integrating with respect to x. This is going to be our first integral. While I'm here, let's go ahead and write out what the second integral is going to be. Our second integral starts at x equals 1/2 and goes until x equals 2, because our intersection point is 2. So from 1/2 to 2. Our upper curve in this case is the curve 2 divided by x, and we're going to subtract out the area under the lower curve, which is the curve 1/2 x dx. So now we've set up all of the integrals, and the easy part happens. We just have to do a bunch of integration. I'll start with a fresh sheet of paper. So for our first integral, the integral from 0 to 1/2 of 8x minus 1/2 x dx. This is easy to integrate because both of these are just polynomials, and I'm going to end up with 8 divided by 2 is 4x squared minus, I'm going to raise the x to the squared power and divide by 2. That makes it minus 4th x squared, evaluated as x goes from 0 to 1/2. So I'm going to plug in 1/2 for x. And then I'm going to subtract out plugging in 0, but we see that when we plug in 0 for our lower bound, we just end up with 0. And this simplifies nicely. 4 times 1/2 squared is a 4th, minus 1/4 times 1/2 squared is a 4th. So that's equal to 1 minus 1/16, which is equal to 15/16. So that's the area on this left portion. The area for the right portion is given by this second integral. So integrating the first term, we can integrate term by term because we're separated by a minus sign. The first term is the integral of 1 over x. If you applied power rule to this, you would see it would be x to the negative 1. We would raise it up to x to the 0. That's not possible. So instead, we end up with 2 times the natural log of the absolute value of x, because the integral of 1 over x is natural log of absolute value of x, and the 2 is a coefficient that's just multiplied. Minus, we already took the integral of this, but we know that we're going to raise the power. It becomes x squared, and dividing by 2 becomes times 1/4, evaluated as x goes from 1/2 to 2. So I have to actually plug in both of these bounds. I'll give myself a little space. So this becomes 2 times the natural log of 2 minus 2 squared is 4 divided by 4 is 1. So that's evaluating it at 2. And now I'm going to subtract off evaluating it at 1/2. 2 times the natural log of 1/2 minus 1/4 times 1/2 all squared. And unfortunately this isn't going to cancel into something that's super nice, but let's look at our terms. I have 2 times the natural log of 2 minus 2 times the natural log of 1/2. If you wanted to, you could plug this into a calculator, or you can know that the difference of 2 logs is the log of their quotient. So this ends up being 2 times the natural log of 2 divided by 1/2. And if you didn't remember this property of logs, that's not a big deal. That's something you can do on your calculator. And then I am subtracting 1, minus 1, and then I'm adding 1/2 squared is a 4th, times another 4 is a 16th. So this would be 2 times the natural log of 2 divided by 1/2 is 4. Minus 1 plus a 16th is minus 15/16. So let's put these two pieces together. We got positive 15/16 for the first piece, and then we got this whole big chunk minus 15/16 for the second piece. And so this plus this, the 15/16 will cancel, and we'll see final sum is just 2 times the natural log of 4. And I'm not going to add a plus c. Why don't I add a plus c? It's because this is a definite integral. This should be an exact numerical value. This isn't a family of functions.